This next segment will cover ANOVA style tests, also known as F tests. We'll have 4 parametric and 2 nonparametric, though we'll also talk about some more nonparametric tests or modifications of parametric tests. So let's start with one-way ANOVA. This tests if at least one mean is different among groups, where the groups are larger than 2 for normal distributed data. So you can think of ANOVA as a logical extension of the 2 means t-test for larger groups. So instead of a 2 means t-test, which looks at the difference between average height of young and old persons, we might have more than 2 groups, like the average difference in height between young, middle-aged, and old persons. So to do this in GPower, we'll now have to start selecting the F tests from the test family, and then ANOVA, Fixed Effects, Omnibus, One-Way. One-Way is the big one here. And then again, a priori. So we'll need to enter, as before, alpha and power, but now also the number of groups. Then, if you have background information, you can do the mean and then size for each group and then the standard deviation. Calculate and get total sample size. If you have no background information, naive, you can run A through C, then guess the effect size before calculating and getting total sample size. So is there a difference in new car interest rates across 6 different cities? Here, the null would be there's no difference, 0%. And the alternative would be there's at least one city that has significantly different rates. Here's some trial information with the means from each city. Can get standard deviation for all of them as 0.786, and then group sizes of 9 here for this trial data. We can enter all this in the determine box. So the number of groups is 6, the standard deviation. Here's the means of all of them, and then the sizes are all 9. You might notice here specifically there's no tails in ANOVA, so you don't need to worry about ANOVA tails. And then when you're calculating things here, if the groups are all equal sizes like ours are, you can actually enter that into this box, click equal n, and it will populate the sizes correctly. So the results here, we find that there's a total sample size of 48, which works out to 8 per group. Here are 2 practice examples for one-way ANOVA. As before, I suggest strongly that you pause this video and work these out yourselves before turning to the answers. Looking at weight loss and white blood cell counts between surgery and medication regimes. You can pause now. For the first example, we are given the data to the right here. You can see that there's 4 groups and 5 group size for each group. Can get the means from this raw data here, and then overall standard deviation of 2.23. This will give us an effect size of 0.61 and a total sample size of 36. Since there are 4 groups, that means that would be 9 samples per group. For number 2, we only have the number of groups, so we're going to guess a median effect size of 0.25 for a total sample size of 200, or 40 per group. Next, we have the Kruskal-Wallis test. which can be thought of as the non-parametric parallel to the one-way ANOVA. Now, in G-Power, there isn't a standard way of calculating sample size for this Kruskal-Wallis test. So I'm going to use the rule of thumb found at this post here, which is to run the parametric test, so ANOVA, and then add 15% to the total sample size. Because non-parametric is weaker, we're going to need more samples to detect a true effect. So we'll do the same thing we did for ANOVA, so ANOVA fixed effects one way under the F-test family, enter all the things as normal, but then at the end here we're going to add 50% to size, so the total sample size plus the total times 0.15. Same thing whether or not you had background information or naive. Is there a difference in draft rank across 3 different months? Null is there is no difference. The alternative is there's a difference in at least one of the months. I don't have any background information, so I'm going to guess that it's a medium effect. And now for F-test, if again you hover over the box, it'll pop up the conventions. We see that for F-test, the conventions are small, medium, large are different than the t-tests. So a medium here, instead of being 0.5, is 0.25. So enter that information in here. We know that there's 3 groups. We'll get a total of 159 samples, so that's 53 per group for the parametric ANOVA. But this is non-parametric, so I'm going to take the total, add 15% to get 182. Since we can't have decimal numbers of samples, we'll round up to 183 samples, which is 61 per group. So once again, we'll notice that the non-parametric, 183 samples, is weaker than the parametric at 159. Here are some practice examples. Pause now and try them on your own. For hours worked and salaries. For practice problem number 1, we're given the information on the side here. We can see that there's 3 groups, group size of 5, and we can get means from this data to get 3 different means and a standard deviation of 8.7. So that will give us an effect size of 0.54, and with a parametric test, the ANOVA is 39. We can multiply that by 1.15. That's the same as taking 39 times 39 times, or sorry, plus here 0.15. So that gets us a total sample size of 45, which is 15 per group. Second question, the only information we have is that there's 25 different departments. So there's 25 groups. Now I'm going to guess a small effect size. And so if I plug that in parametrically, it's 2,275, but then we need to round up, or sorry, add 15% and then round up to get a total of 2,625, which is 105 per group or department. Next, we have repeated measures ANOVA. Test is at least one mean is different among groups, just like ANOVA, but these groups are now repeated measures. So it's like the logical extension of a paired t-test for more than 2 groups. Like for example, if patients are tested for blood pressure at not before and after treatment, but say 1, 2, 3, and 4 months post-treatment, more than 2 groups. In G-Power, this is under the F test, but now it's ANOVA repeated measures, and we'll select within factors. For this, there's a lot more going on, so I'll briefly go through the information you'll need to add, but then we'll look at the next page for the parameter calculations. We'll need alpha and power, then the number of groups, and then the number of measurements. Let's look at that in next page. We'll need correlation and this non-sphericity correction. And then under determining it, we can enter a calculated partial eta squared, which we'll see more in next page. To do this, you're going to actually have to go under background. So if you have background information, you'll enter it calculated from something such as an SPSS. You have to set that. We'll take a look at that in a couple examples. And that's under the options bar, and then that has the effect size specification. Now, naively, you just guess an eta squared based on convention. Keep that, but you'll need to keep the effect size specification from that options bar as in G-Power 3.0. You also have to guess your correlation. Once you have all this entered, you can calculate it and get total sample size. So let's look at some of those parameters more in detail, how to get them. So we'll need to enter both the number of groups and the number of measurements. Groups are how many different groups are being subjective. In the simple case, the only case we'll look at today is that there's just one group, so say college students. Then the number of measurements is the number of repeated measures. So like the number of times blood pressure is measured. Then the core among repeated measures is the correlation. So this is very easy to get, like the paired t-test correlation. What you can do is average across all the values from, say, a correlation table. So average all the correlations between your measurements. Another way is you can default it to 0.5 unless you have reason to believe it's different. Another parameter is the non-sphericity correction. This is the assumption of sphericity. If the data is assumed to be spherical, you can enter 1. And this can actually be estimated with background information. A lot of times there's a sphericity test you can run in things like SPSS. And what it means to be spherical is essentially the variances of the differences between all possible pairs of the within subjects should be equivalent. Now finally, this is the big one, the partial eta squared. This is the proportion of the total variance in a dependent variable that's associated with membership of different groups defined by an independent. So this is closely related to effect size. So the larger the eta, the larger the effect size. So this can be measured from background information. A lot of times you can get a ANOVA table out, and the equation for an eta squared is the sum of squares of the between groups or effect, and then the total, which is the sum of the sum of squares between the effect and the error. So that gives us the total here. So sometimes also written as sum of squares of total. So if you don't have any background information, you can guess the eta squared, just like you could guess effect size. And the conventions for eta squared is, at least in G-Power 3, is 0.02, 06, and 14, or 0.14. As an example, is there a difference in blood pressure at 1, 2, 3, and 4 months post-treatment? So the null is there's no difference, and the alternative is there's at least one difference. So there's only one group here, but 4 different measurements. I have no background information, so I'm going to just guess it. So I'm going to set a small partial eta squared, so 0.02 here, which will spit out an effect size for me. And I will set a correlation of 0.5, kind of the default, and then assume that it's spherical. This gives me a total sample size of 69 needed, and then each of those samples are going to have those 4 measurements, the 1, 2, and 3, 4 months post-treatment. Here are some examples for repeated measure ANOVA. Take some time to try these yourself for blood serum levels and antibody levels. So for the first one here, we have data on the right. So see that there's just one group because we're looking at just patients, and then 4 different measurements. Now, I took this information, ran repeated measurements in SPSS, a test, to get an eta squared based on these values. And so these are the values I got. And then this was the eta squared of 0.92. And now I selected as an SPSS in the options bar. And part of this test, sphericity was non-significant, so I can set it to the correction to 1.0. So if it's non-significant, it's non-spherical, it's 1. If it is significant, you have to have a different correction. So my effect size was 3.39, total sample size of 3, so there's very big difference here. For the second one, all I have is the number of measurements, so one group 3 measurements, so I'll guess a medium eta squared, but since I'm guessing and not calculating from, like, say SPSS, I want to make sure in my options my as in G power 3.0 is set up. I'll default my correlation to 0.5 and assume it's 1.0 to get an effect size of 0.25 and a total sample size of 27. Moving on here, we have the Friedman test, which is the nonparametric version of repeated measures ANOVA, or the logical extension of the 2 means Wilcoxon. Data is paired, there's more than 2 groups. So just as in the Kruskal-Wallis test, which was the nonparametric analog of the one-way ANOVA, there really isn't a way to do this in G-power, so we'll take the correction factor of 0.15 or 15% like we did before. So we'll enter all the things we need, whether with background or naive. Once we get the total sample size, we will add 15%. For the example, is there a difference in taste preference across 3 different desserts for a group of students? You see that the null is there's no difference, and the alternative is there's at least one dessert that has a differential preference. So it's just one group, a group of students, and then 3 different measurements because we have 3 different desserts. Using a trial study with some data, found a sphericity of 0.88, and then an eta squared with sum of squares of the effect and then the error, so the total there, so eta of 0.31. So because I was taking data from information in SPSS, so this data was from SPSS, we need to go to options, which will pop up this box, and we'll need to choose in the options as an SPSS, click OK. And so then when we enter this eta squared, partial eta squared over here, it'll give us the correct effect size. And that will give us a total sample size for the parametric at 15, but since we need to get the non-parametric, we'll get 17.25, round up to 18, so we can have 18 samples are needed, a whole number, and then each of those, of course, are going to get 3 different treatments, or 3 different measurements. Here are some practice for the Friedman test on taste preference and movie preference. For the first question, we have data here. See that there's four different groups. Or sorry, one group, four different measurements. So I took this data, put it into SPSS to get our partial eta squared. So it ended up getting the sum of squares of the effect, and then the effect plus the error. We get 0.95. Then I went and made sure to select as an SPSS in the options. Sphericity was non-significant, so the correction is 1. So we get a large effect size, a parametric of sample size of 3, but I need to correct and then round up because you can't have 3.45 people. You can have a total sample size of 4. For the second, I have no information other than the group and measurement size, so I guess a large effect, but make sure, since I'm not calculating from SPSS, to return it to as in G power 3.0. And default these values, an effect size of 0.4 and parametric of 9, correct for non-parametric to get a total sample size of 11. Now, let's take a look at what we call Multiway Anova, but specifically only one category of interest. So this is extensive ANOVA, where you could have more categories. So instead of looking at age, so young, medium, old, you could look at age and occupation, doctor, nurse, anesthesiologist. But for this type of ANOVA, we actually only care about one category, and we want to control the other categories. These are often known as blocking effects, nesting effects, or random effects. A good example of this is there a difference in treatment, so drugs A, B, and C, from a series of 4 different hospitals? So we might call this a blocks. We're not interested if there's a difference between hospital sections, but we're aware that those might have effects. So we'll account for this to control for variation, so we can actually more accurately tell if there's an effect of our category we're interested in, say, drug treatment. So for this kind in G power, we're going to need to do fixed effects, special effects, main effects, and interaction. Now, if you have background information, as usual, alpha power, and then you'll have to enter the number of groups and numerator degrees of freedom. And since we're only interested in one category of interest, this numerator degrees of freedom is going to be for the category of interest only. So that's pretty important. We'll need to get partial eta squared if we have background information. If not, we just estimate the effect size and get total sample size here. So let's talk a little bit about the number of groups and the numerator degrees of freedom. So the numerator degrees of freedom is the degrees of freedom for the effect you want to test. So to get this, you take the number of categories for the predictor variable or interaction and subtracting 1. And then for interaction between variables, the degrees of freedom need to be multiplied together. So let's take an example. You have a design where there's 3 different seating locations and 2 genders. If you're just looking at seating location, you would take the number of locations, which is going to be 3 minus 1, so that's 2 degrees of freedom. If you are looking at just gender, that's 2 genders minus 1. That's just 1 degree of freedom. But if you're looking at the interaction between the two, it's going to be degrees of freedom of the first and then the second. So 3 minus 1 equals 2, 2 minus 1 equals 1, and then that's 2 degrees of freedom. Now, for the one category of interest, Multiway Anova, we only are interested in a single category, so we'll just use that category's degree of freedom. Like, say we don't care about location for this example, we just want gender. We will, or sorry, in this example, let's say we only care about the location and we just want to control for gender, we would use this location's degree of freedom, which is 2. So that's how you get degrees of freedom. Now for the number of groups, it's found by multiplying the number of levels in both predictor variables. So here we have two categories. So we have genders, which has 2, and then 3 seating locations. So the number of groups is 2 times 3 equals 6. Okay, so we talked about controlling for categories. Well, what categories, what does it mean to control for something? Well, I've already mentioned that you only care about one category, say that drug type. But there's other factors that might interfere with your ability to detect that, because there's variation from those categories. So gender might be interfering, location, age, etc. A lot of times there's 3 kind of classes of effects that are controlled for in ANOVA that you might see these. The first one is blocking. So samples from different blocks, a lot of times location. Like for example, with these mice, maybe they're in different cages, different areas. Another thing you might control for is nesting. So samples are located within different higher order variables, so like leaves nested within branch, or maybe the example here, that this is actually 3 levels. You're maybe looking at weight and height, which is kind of going to be nested in male and female differences. Another one, this is more in the agricultural research, but kind of classical, is split plot. It's more complicated, where there'll be multiple levels. So like maybe pesticide treatment in greenhouse trays across whole and subplots. So here's an example of this sort of split plot design where there might be multiple levels. Let's take a look at our example now. Is there a difference in treatment from a series of 4 different hospital sections? So the category we're interested in is our treatment. We want our control for the variation found in the different hospital sections. We call these blocking. So I have no background information, so I'm going to assume a medium effect size. So for an F test is 0.25 here, so I'll enter that there. Standard alpha and power. And then for the numeric degrees of freedom, that's just the number of treatments minus 1, so that's going to be 2. And the number of groups is the number of treatments times the number of sections or blocks, so that's 12. So I'll enter those here. That gives me a total of 158 samples needed, so that's 13.7 per group, so we'll want to round up so we have even number of people per group, so that's 14 per group, or a total of 168 total. So you notice here a lot of times if you have multiple groups, the sample size they give you, you might have to round up to get whole numbers. So we talked about the one category of interest. We can also do the Multiway Anova with more than one category of interest. That's where you're actually interested in multiple categories. You're not trying to control for it like as in the blocking. This is, if there's 2 categories of this, we often call this Twoway Anova. If there's 3 categories, 3-way Anova, etc., etc. Obviously, the more categories, the more sort of 2, 3, 4-way, the more complicated your design is, the more samples you're going to need. So you usually want to limit it to probably 2 or 3. So an example might be, is there a difference in treatment across age and, say, cancer stage? Sort of this is very similar to the Multiway Anova with one category of interest. We're just going to select Anova, fixed effects, special and main effects, enter alpha and power, And now we still need to enter the number of groups and numerator degrees of freedom, but the degrees of freedom here will be for all categories of interest rather than just the one category of interest. Get partial eta squared. If we have background information, if we're naive, we'll just estimate effect size. So taking our example, difference in treatment across age and stage. Our null is that there's no difference across any of these, and the difference for the alternative is there's at least one kind of combination that has a difference. So we're interested in all three treatment, age, and cancer stage. This is information, say we have a trial study information on, and we find a very small eta squared of 0.0042. Now, to get the numerator degrees of freedom, because we'll multiply all our degrees of freedom because we're interested in all of these. So it's going to be 3 minus 1 because there's 3 treatments, 3 minus 1 because there's 3 ages, and then 5 minus 1 because there's 5 cancer stages. 2 times 2 times 4 equals 16. The number of groups is going to just be the number of treatment, age, and stage. So 3 times 3 times 5, total of 45, which we'll enter here. Now our partial eta squared is very small, and it gave us a effect size of 0.06. That'll be calculated up here. So what we end up getting here is a total number of 4,582 samples. So that's 101.82 per group. So we'll need to round up so we get whole numbers to get a total of 4,590 samples. So very small partial eta squared, very large sample size. So just as in the one-way ANOVA or the repeated measures ANOVA, there really isn't a non-parametric option. So you can do two things from there. First, you could turn to a more sophisticated model for your statistical test, like a generalized linear mixed model. We'll talk about that at the end. Or you can do like we did for the other ANOVAs, run a parametric test and then add 15%. To explore this, I have a table here of what it would look like to reanalyze some of our previous questions. So the one category of interest, we're looking at difference in treatment and controlling for section. We got a parametric sample size. We correct for with 15%. We end up getting a 25 per group, which is a total sample size of 300. So you see it's obviously larger. Same thing for the multiple way ANOVA with more than one category interest. That's more than one of the categories being treatment, age, and stage. We originally had over 4,000. With the non-parametric correction, it's over 5,000. So that's how you would use non-parametric multi-way ANOVA. Let's round this out with some practice of multi-way ANOVA. Try these yourself before moving on to the answers. Here are the answers here, very similar to our examples. But for the first one, we have information found on the right here, and we know that we want to control for age, so we're only interested in treatment. So our numerator degrees of freedom will be the number of treatments, so 3 minus 1 equals 2. And it looks like we have 3 age groups and then 3 treatments, so that number of groups is 3 times 3 equals 9. Taking this data, putting it in SPSS, running proc univariate, you get sum of squares out to get a partial eta squares of 0.14, which will give us an effect size of 0.84, using the as in SPSS in the options to get a total sample size of 19, which we'll have to divide through by the number of groups. For the second one, we're giving no information other than we're interested in treatment, age, and cancer stage. So we can get the numeric degrees of freedom as 16, number of groups is 45. I'll guess a medium effect size, that sounds fine. So we'll have to do that as in G power 3.0 for a total sample as a 323, which we'll need to divide through by the number of groups. With that, that concludes our ANOVA section for sample size calculation.